Now I would like to calculate the susceptibility of a paramagnet. And basically we're going to use again Langevin theory. Now non-interacting magnetic moments on atomic sites are randomly oriented as a result of their thermal energy when in the absence of a magnetic field. So that's what we know from our previous video. And if a moment makes an angle theta with respect to the applied field, there is going to be an energy associated with this moment. So for a moment that makes an angle theta, with respect to the applied field, we know that there is an energy associated with this. We can write energy of this moment will be minus m dot h. This is using CGS. Or we can write energy is minus mu 0 m dot h using SI units. Okay. And since there is an energy associated with the orientation of the moment with respect to the field, using the Boltzmann distribution, the probability of occupying a state with energy E is proportional to e to the minus energy divided by kBt. This is Boltzmann distribution. For Boltzmann distribution to be applicable, you need to have a system that is in contact with a thermal reservoir, and that's exactly what we have. We have a localized moment that is in thermal contact with the rest of the lattice, so it's going to be obeying the so-called canonical distribution. Okay, so this Boltzmann term then will become using CGS units. So we can write this probability of having an energy E will be proportional to e to the minus m dot h over kBt, or we can write this as e to the mh cosine theta over kBt. So we're interested in how this angle theta is distributed. So let's leave this for a moment and think about the angle theta. We know that in classical mechanics, the moment m can make any angle theta with respect to h. In quantum mechanics, we have discrete angles possible, discrete values of theta given by the quantum number capital M sub j. Okay, so for a moment I'm going to think that all angles have the same energy, so I have a uniform distribution of angles because I have these randomized moments right at the beginning, and when I turn on the magnetic field they can have any angle with respect to the magnetic field, and assuming that there is no energy associated with the angle, I can think of a uniform distribution of angles. So initially what I'm doing here is wrong, but we're going to start with this. If all angles had the same energy, then we can write P of theta, probability of having an angle between theta to theta plus d theta would be given by the area of this strip divided by the total area of the sphere. So you can see that this angle theta can take values between 0 and pi, and for each angle value I have a strip here that is on this spherical surface. So the probability of having an angle P of theta that is probability of having an angle in the range theta to theta plus d theta. This is going to be, of course, it's P of theta times d theta in that case, because I'm giving a range, P of theta d theta. So the d theta is chosen so small that the probability is the same for angles between theta and theta plus d theta. Well, that's if you think about the area of this region, so I see that I have a radius r here, so this is the radius r. So if you change the angle by d theta, this portion will be r d theta, and then you have the circumference of this circular region. So you have the projection of this radius here, that is r sine theta. So this circumference of this circle will be 2 pi r sine theta. So 2 pi r sine theta multiplied by r d theta will give me the total area. So this total area here will be equal to, so dA is 2 pi r sine theta r d theta. Okay, and this divided by the total surface area of the sphere will give me the probability of having an angle theta, because it's a uniform distribution of angles, so I'm assuming a random distribution of angles. So this would give me 2 pi r sine theta multiplied with r d theta divided by 4 pi r square, that is the surface area of a sphere, surface area of a sphere where I can have all possible angles, is 4 pi r square, and I note that this angle theta with respect to the field axis has to change between 0 and pi, so that I will be covering the full sphere. Okay, so that is basically giving me for P of theta d theta 2 pi r square sine theta d theta divided by 4 pi r squared. Okay, so this would be the probability distribution. So it would actually give me at the end sine theta over 2 d theta. So this would give me sine theta over 2 d theta. if you integrate from 0 to pi p of theta d theta, what would you get? You would get 0 to pi sine theta d theta over 2. That is minus cosine theta over 2 between 0 and pi. For pi it is minus 1, so minus minus 1 plus 1. And then I have minus minus plus cosine 0, that is 1 over 2, which is 1. So this probability would be well normalized as expected. Okay, so, but each angle has an associated energy. So this is not the right way to think about the probability distribution of angles. So we have to weight the angular distribution with the corresponding Boltzmann factor e to the minus e over kbt. So we have to say that the probability of having an angle between theta and theta plus d theta, probability distribution function, will be not just 2 pi r square sine theta d theta multiplied by the Boltzmann factor e to the mh cosine theta over kbt, 2 pi r square sine theta d theta, and divided by integral, not just the surface area, we have to integrate over all possibilities, e to the mh cosine theta over kt, kbt, 2 pi r square sine theta d theta. This is actually the partition function that I'm writing. So if you know from statistical physics, this is actually partition function. So I'm using the canonical distribution. Okay, now I can see that there is a simplification in this, because the integral is over the angle theta, so 2 pi r squares will cancel. So at the end I will get, for the probability distribution function p of theta d theta, this would be equal to e to the mh cosine theta divided by Boltzmann constant temperature sine theta d theta divided by the partition function 0 to pi e to the mh cosine theta over kbt sine theta d theta, where the denominator covers all possible angles. Then, in order to calculate the total magnetization, M, magnetization will be equal to the number of atoms per volume, the magnetic moment per atom, and because the magnetization comes from the projection of the magnetic moment onto the field axis, cosine theta, so I take the average value of cosine theta. So this N is number of atoms per volume, M is magnetic moment per atom, and theta is the angle between M and H. So we're taking the projection of M onto the field axis. And in using Langevin theory for diamagnetism, basically we talked about this. Avogadro's number times the density of the material divided by the atomic weight gives us the number of atoms per volume. So this is capital N. So let's put a V here just to make sure that it's number per volume. So this is a mass per volume. Atomic weight is mass of 1 mole, and 1 mole contains Avogadro's number of atoms, so the masses cancel. We obtain here number of moles times Avogadro's constant, that is the number per volume, which gives us the number density, because the masses will cancel as well. So that is the number density. So how do I calculate the average value of cosine theta? Well, I have to use the probability distribution, integral over all possible values of theta, 0 to pi, cosine theta, probability distribution function, p of theta, d theta. So if I perform this for the magnetization, I will find the number density NV times m, integral from 0 to pi cosine theta p of theta d theta, which is the number density times magnetic moment per atom m, integral from 0 to pi e to the mh cosine theta over Boltzmann constant times temperature, and I had this multiplied by sine theta d theta. Now I have a cosine theta here, cosine theta sine theta d theta, divided by the partition function, integral 0 to pi e to the mh cosine theta over kbt sine theta d theta. Now, in order to perform these integrals, let's call mh over kbt y. So I define this as y. And with that, mh cosine theta over kbt, which is y cosine theta, I will call x. And minus y sine theta d theta will become dx. And when theta goes from 0 to pi, when theta is equal to 0, I will have cosine 0, so x is equal to y. So this would mean x is equal to y. And when theta is equal to pi, cosine pi is minus 1, x would be equal to minus y. Okay? So then I can write this integral as the magnetization is equal to integral from 0 to pi, since I have changed the change to the variable x and y here. So when the theta is equal to 0, x is equal to y. So this is going to be from y. When theta is equal to pi, x is equal to minus y, e to the mh cosine theta over kt, that is e to the x. And then I have cosine theta is x divided by y, that is cosine theta. And sine theta d theta is minus dx divided by y. And in the denominator, I have from y to minus y, e to the x, and for sine theta d theta, I have minus dx divided by y. So this is going to become Uh, of course, I have a factor of n and m here. So this is going to become nm. You see, I have one of the y's disappearing. Y is not a variable, it's a constant here, mh over kBt, for a constant temperature. So one of these y's will disappear, and I will obtain n times m and v times m over y. The integral from minus y to plus y of e to the x dx, and in the denominator I have the integral from y to minus y of e to the x dx. So this will give me number density, magnetic moment per atom, divided by y, integral from minus y to plus y, x e to the x dx. And here I can perform this integral. The integral of e to the x dx is e to the x from y to minus y. So to perform the integral on top, I have to do integration by parts. So I'm going to call dv e to the x dx, so that v is e to the x and u is x, du is dx. So remember, integral u dv is uv minus integral v du. So we have integration by parts. Integral of u dv is uv minus integral v du. So we're using this mathematical expression. And this is to perform the top